when I'm on the verge of scrapping a part, the rationale that I always use to attempt to repair it is, well, I can't make it any worse. Incorrect. Never underestimate my ability to make a problem worse. This is just a disaster. What have I done? Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive this week. We're going to finish up the main locomotive frame. That's going to include rear axle boxes, suspension mounts, lots of little details like that. And well, sometimes the simplest things can go very wrong. Let's find out how right now. When last we left our locomotive frame, it looked very much like this. Two hopefully identical side frames. Now we got to join them all together with that pile of scrap metal that you see behind it. Luckily, I had all the pieces in my scrap bin needed to do this. Step one is going to be to bore out that rear axle box. I really should have done this before separating the frames, so I have to rejoin them to do this, because those axle boxes really have to be perfectly aligned, obviously, across the frame. But luckily, there's lots of reference holes on this thing that I can use with some gauge pins and some clamps to get the two pieces back together and perfectly aligned. Setting them up in the mill now, I need to get the spindle directly over where that bore needs to go. I can't reach the reference point that I used for all the features on this frame. I can, however, reach the other axle box. So I'll center up on this and use this as my reference. And honestly, this is probably a better reference because one of the most critical dimensions on locomotive frames is the distance between the axle boxes. Because of course you need the center lines of the axles of all the drivers to be the exact correct distance apart. Because on a steam locomotive, the drivers are all connected by rigid components. You've got the connecting arms, you've got piston rods, you've got valve gear, all that sort of thing. So this distance between the drivers needs to be as accurate as we can get it. I did a little test spot with the center drill because I also need to make sure I'm dead nuts centered on that split line between the frame and the insert piece, the T-shaped block that goes in there. Because when we're done, this bore has to be split perfectly in half by that separation line. It looks good, so I will drill my way up in a couple of sizes. The drawings call for this hole to be reamed 9/16, but I don't actually have a 9/16 reamer, so I'm going to have to do the final finishing cut with the boring head. So I brought it as close to dimension as I could with drills, Price is Right rules, as close as you can get without going over, and then in comes the boring head. Touch off, move the head clear, dial in some depth of cut, and away we go. Regular viewers will know that I have kind of a love-hate relationship with boring heads. If you're not a regular viewer, why not? Were you some kind of jerk? Sorry, I don't know where that came from. What I meant to say was that boring heads are kind of tedious and kind of annoying and more difficult to get good results with than on the lathe, but when you need a boring head, nothing else will work, such as right now. I snuck up on that dimension courtesy of my telescoping bore gauges, dialing in a little bit of cut at a time. I only had a couple of passes to make here because I got really close with the drills, so that made the boring head actually quite a bit more enjoyable than usual. If you have to do like 20 or 30 passes, or if the hole is really deep and you don't have power down feed, well, then you're in boring head hell. When they work though, boy do they work. I got an excellent finish in there. My target dimension was 562.5, and that, my friends, is 562.5. Now that dimension wasn't actually that critical because we're going to be making bearings to go in that hole, which could be made to fit, but hitting a dimension never gets old. Little cleanup, some deburring, and I'll pull these apart so you can see what a neat feature this rear axle box really is now that it's done. Full circle, half circle, full circle, half circle, full circle, half circle. You get it. Now, one of the nice things about this design is that we can make a split bearing that goes in here, and we can adjust the tension on that bearing with this block and potentially compensate for wear. Now, I don't think that's actually how this block is going to get used in this design, but in principle, you could do that. On now to the front bumper or bolster of the locomotive frame. I believe the Brits would call this a buffer beam. A buffer beam. but we don't have buffers on North American rolling stock or locomotives. The buffering on our railroad equipment is done by the couplers. The couplers are shock mounted and do the buffering for us. So we don't call it a buffer beam. We just call it a bolster or a bumper or a pilot mount or, various other things. It's a little brassy, squarey bit that goes at the front. I think that's the technical term in this case. I had stock the dimension for this, so this was nice. All I had to do was square up the ends. And because the piece is wider than my vise, this is always extra handy because you can do both ends in one setup, and you don't have to measure the length because you can zero the DRO after the first cut, then move down the length of the part plus the diameter of the end mill, machine down to that point, and your part will be the correct length. It's still a good idea to start measuring when you get close to that dimension because there is going to be deflection in the quill and or the end mill, and the accuracy of the dimension of the end mill itself depends largely on how much you paid for it, so your piece is likely to be a little bit over length if you just go by the DRO strictly. After this is a whole bunch of mounting holes that are tapped and threaded for various things. The main ones are for attaching this bolster to the front of the frame, and then there's mounting holes for the coupler pocket and the footboard that goes on the bottom of this. A whole bunch of drilled and sometimes tapped holes. Not super exciting. What is exciting is that some of these holes are countersunk, so I get to use my shop-made D-bit ground countersinking tool. And let me tell you, a perfectly countersunk bolt never gets old. There's a bunch of features on all four sides of this piece, so I did make heavy use of an end stop so that I didn't have to redo my edge finding. I could use the same X and Y positions on my DRO for all four sides of the part because I can rotate it, put it up against my end stop, which saves the X position, and of course the fixed jaw on the vise is saving the Y position. These holes on the end are a bit curious. They are ostensibly threaded holes that hold a pair of handholds that go on the front corners of the locomotive. However, the drawing calls for the tap drill size to go all the way through, even though the threads are actually only in the top third for mounting the handholds. The drawing is very clear that that hole should go all the way through. I looked through all the rest of the drawings for this locomotive, and I could not find any reason why that hole is supposed to go all the way through. However, while I couldn't identify any functional reason for that, I think there is a setup reason to do it, and so I did it. It certainly won't hurt anything. The through hole won't be visible from the top. It's only on the bottom where you can see it, where you can't get your head in under there because it's a 3.5-inch gauge locomotive for crying out loud. But I anticipated what I think Koza was thinking, which is that it's going to be much easier to do an upcoming operation if that's a through hole. A couple hours of machining later, we have a very nice piece of square bar with a whole bunch of extremely accurate holes in them, not including those little center drills which are not in the right place. And it's also on the bottom, so that'll be our secret. The rear bolster is very similar, a smaller piece, a little bit shorter, but a bunch of holes, yada yada. So here's the two bolsters, looking very good. Now the lower one is supposed to be shorter, so nothing wrong with that. However, there is something else wrong here. Do you notice it? Those countersunk holes are for mounting the frame rails, so wouldn't it make sense that they would be the same distance apart? Swarfy here will poop on my mistake to identify it for you. Yeah, somehow I misread the drawing and I drilled the holes on the front bolster too close together. So I thought, well, I've basically scrapped the part at this point, but maybe I can repair it. I thought I'll try silver soldering some screws into those holes because a screw is the perfect shape to fill the hole and the countersink all in one go. If I do this well, then the silver solder will sand smooth with the brass and it's all going to be powder coated in the end anyway. You will never be able to see this repair, and silver solder is actually stronger than brass, so this repair won't weaken or damage the part in any way. So, done well, this will be an invisible and flawless repair. Now, the words done well are doing a lot of heavy lifting in that sentence. I started out using way too small a torch. I don't know why I thought I could do this giant heavy piece of brass with my smallest torch. I think the reason I thought I could do this was because I thought, I'm very lazy today and I don't feel like going outside to the outside storage to get the big propane tank so I can use the right size torch for this. Just when I was starting to wonder, how am I going to make drilling a bunch of holes in some square bar into an interesting video, I should have known I can always count on my own incompetence to create content. Because I'm using too small a torch, the silver solder is just not flowing at all, and I made a terrible mess of this part. I pickled it and cleaned it up and filed down the solder anyway just to take a look at it, but I already knew this was going to be no good. No solder made it through those threads, and in fact the threads were still loose in there. I could poke them with a pick and wiggle them around. So that was a terrible repair. I thought, well, before I scrap the part, I'll try one more time with the proper size torch. Everything's clean and pickled now anyway. Got out the propane tank, got out the big torch, and let's do this again properly. What a difference having the right torch for the job makes. This thing went great. It heated up quickly, the solder flowed beautifully, I got really nice looking joints all the way around. This was so much better. And of course this took 10 times as long as it would have to go get the propane tank in the first place, which is what I was trying to avoid. You might think the moral of this story is, don't be lazy. No. The moral is, the answer to life's problems is always a bigger torch. And that second repair cleaned up beautifully. The silver solder is a different color, of course, you can see it, but it's filed smooth to the surface of the brass, and that's all going to be powder coated, and it will be invisible in the end. I'll give you another look at that repair so you can see it close up in a second, but I'm going to re-drill the holes now in the proper place, and if I did my job right, the inside of that bar where those holes were incorrect is now all solid silver solder and or brass, and so this should drill just as though it was original material, which in fact it did. If you look closely, you can see the original screw heads in there, where the silver solder has kind of filled in the screwdriver slot, but underneath the holes are completely gone, and there's no sign of those old holes ever having been there. I also used some magnification and inspected the insides of the new holes, just to make sure there wasn't any voids in there or any encroachment of bad repair, but it looks like solid brass all the way down, so the repair was effective. The solder went all the way down, filled in the holes, and once again, it's like brand new brass all the way down. Next step is to round the ends of the front bolster, which is what those center holes are going to be handy for. Of course, the top ones are threaded, so that's not a good reference, but those through holes through the bottom will be good references, which I think is what we were all thinking here. I've got this end rounding tool that I made for my rotary table. I've got a video on making this if you're interested. It has these centering pins. Now, I don't have one quite the right size. This one's a little too small. So I'm going to make up a new one. These pins are quick and easy to make, which was one of the design goals that I had for my end and corner rounding system for the rotary table. I've tried to make this as quick and easy to set up as possible, with the hopes that I would use it for rounding the ends of many things. It turns out to be still a fair bit of work to set up. Rotary table setups are a lot of work. There's only so much you can do to speed them up, but this does help considerably. However, I still only use it for bigger end rounding jobs like this one. I'll get my rotary table on there now. This thing has keys on the bottom of it, so it aligns with my T-slots. If you haven't made keys for your various fixtures, do that. That pin that we just turned goes into this fixture in the center, which is a Morse taper mandrel that I also made that goes in the center of my rotary table. The middle shoulder on that pin is a standard diameter, so it will go in a collet, and that allows me to use it to center up the rotary table on the spindle, which is one of the more time-consuming parts of a rotary table setup. So I can line that up by feel. Then the pin comes out of the collet and goes back into the center of the rotary table, and that middle shoulder is also the same height as the thickness of my parallels, so the piece can sit on there on the centering pin, which gives clearance for the end mill. Now with the rotary table set on 0, I need to get the workpiece aligned with the y-axis, so I dial in the piece and then clamp it down in this position, and now I can use my rotary table to direct a 180-degree cut all the way around the end of this thing. I needed a little bit of room for the clamps. Some pieces are easier to clamp than others on the rotary table. Clamping on rotary tables is often a challenge, so often I'll end up doing something like this where I've got one clamp on there and I do 1/2 of my curve at a time. Then when it comes time to do the other side, I add a clamp, then remove the first clamp so the piece hasn't moved and I can do the other half of the curve. This first cut went pretty well. The two curves don't quite line up. There's just a wisp of uncut material in the center, but I'm going to leave that alone. Little errors like that are common in rotary table setups because rotary table setups are very much an accumulation of tiny errors. If your rotary table isn't perfectly aligned with your spindle, or the pin isn't perfectly aligned with the center hole on your piece, or if the center hole in your piece isn't perfectly aligned with the sides of the piece, or if the piece wasn't perfectly aligned with the y-axis of the mill, all these little errors add up, so it's very difficult to get them to come out perfectly every time. However, you can get them very close, as I did there, and a little bit of blending on the Scotch-Brite wheel hides all the crimes. Next up is quite a critical set of features. We need a pair of grooves in each bar that will hold the ends of the frame rails. So the book suggests this setup here, a stack of parallels with some packing underneath the smaller rear bolster to bring them up close to the same height, and we're going to machine all the grooves in one setup. The depth of the grooves is actually slightly different, and the pieces are different thicknesses, so that packing material is calculated to create the correct offset at the tops of each of these. So they look like they're at different heights, and they are, but that's intentional. To get the setup aligned, I've got a gauge pin that's the same diameter as those holes, and I line up my spindle on one of them. I zero my x-axis right there. Then I move over to the opposite hole on the same bolster and line it up there, and I use the half function on the DRO, so I'm finding the center line similar to how you might do with an edge finder. Now I'm going to come down and line up this hole on the lower bolster. It should be in the same place on X, but of course it isn't because I just slapped them in the vise. And I'll tappy tap tap the other piece until it aligns with the same X value as the other bolster. And I had to do a little bit of wiggling, tapping back and forth until I had all 4 reference holes on the 2 bolsters in exactly the right places all the way around. So now they're all perfectly aligned, and I've got a perfect center line down the middle of both of them. Next, we have a little bit of a challenge with the width of these grooves. Nominally, the frame rails are supposed to be 1/4 of an inch thick. However, the material that I used happens to be exactly 3/1000 oversize. And this is common because the sides are not machined, that's factory stock, so they're a little bit oversized. Now, the question is, though, where do we put that extra width? Where we cut these grooves is going to determine where the extra thickness on the frame rails is going to land. By coincidence, a viewer who built an A3 reached out to me recently and said that he had the same issue, and he decided to hold the inside dimension, so the inside surfaces of the frame rails land where the drawing says they should. And he said he regretted that. He wished he had held the outside dimension instead. And after he said that, I put some thought into it, and I think he's right. It makes more sense to hold the outside dimension because on a steam locomotive, it's the outside dimension of the frame rails that's more critical. The outside dimension sets the thrust surfaces for the bearings, which sets the distances between the drivers and all sorts of other important things, whereas the insides of the frame rails are just mounting surfaces for water pumps and things. So there's really very little that's critical on the insides of the frames. So that's what I decided to do. I'm holding the outside dimension, and I'm gradually widening the insides of my grooves a little bit at a time until I have a perfect snug fit on those frame rails, and I know that my outside surfaces are right where the drawing says they should be. And the other side was the same way, and it was easy because now I know how much width on those slots I need to add for that perfect fit. Great, grooves are looking nice, but now I need threaded holes in the ends of the frame rails to bolt those to. That's tricky. I've only got one machine that can handle pieces this long in order to drill holes in the ends, and that's my drill press. So drill press setup it is. I've got a toolmaker's vise on its side, which is going to guarantee squareness in the XY plane. Then to line up the spindle, I'm going to have to wiggle it around and line it up kind of by eye. So I'm using the bolster as a drill guide since I can't get accurate XZ placement on the drill press. I line up the clearance drill size with those holes in the bolster, then clamp it down, and now I can use the clearance drill as a centering tool effectively. I go down into the bottom of my hole, and I start the drill up, and I just touch the material down there, and that's going to make a dimple that's well centered because the clearance drill is held centered by the clearance hole. Then I swap out for the smaller tap drill size, and that's going to go down and self-center on the dimple that the other drill made, and we don't have to worry about that drill wandering, since I can't get down in there with a center drill. For depth, I've marked the desired depth of my hole plus the thickness of that bolster area that's above the end of the frame rail. I've marked that on the drill itself, and I'm just drilling down to that Sharpie mark. Luckily, the accuracy of the depth of these holes is not critical. And then I wiggle it over to the other side, put the clearance drill back in, and do all of that again for the second hole on this frame rail. With the drilling done, I took it over to my bench vise, and I'm going to once again use those clearance holes on the bolster as a tap guide. I can go right down through there and tap the drilled hole that's at the bottom. I could have done this tapping in the drill press, but I would have had to move the table down, and it's a round column machine, so moving the table would have cost me a bunch of setup time, whereas I can just use it as a tap guide, tap it by hand, and Bob's your uncle. 2 tapped holes in exactly the right place. Okay, let's do some assembly now. I can get this front bolster lined up on there. These frame rails are quite a snug fit. I'm very pleased with how well they fit, but they do require a teeny bit of encouragement to get lined up and make sure things are square top and bottom. I want the top surface of these frame rails to be flush. That's important. And if I did my job right, these screws should go right in perfectly, which they do. I am very, very pleased with that. That really could not have gone better. That is one of the better fits I've achieved on this project so far. Very, very pleased with that. The rear bolster is next. It also is a very snug fit, so it was encouraged into position with a little bit of clamping to get the surfaces flush, and then a little bit of percussive persuasion to get it to sit down all the way. My drilling and tapping procedure was the same, but I could do it on the mill because these holes are vertical. Since this rear footboard sits up on top of the frames, it actually forms the rear of the cab floor, so that's why it's up high like this, and that is much easier to do over here in the mill. Let's do some inspection before I make the rest of the cross members. I'm checking for parallelism, and actually all the way down I've got within 1/1000th, so that's excellent. And then a squareness check by checking the diagonals, and both diagonals are within 1/1000th of each other as well. So that is a pretty fantastic result. That really could not be straighter or squarer if I tried. I cut and machined the cross members out of more excess frame material because I didn't have any other suitable stock. I machined these as a pair because it's important that they both be as identical as possible. And in fact, I got the length so good on those that they almost sit in there under friction. They're actually sitting on burrs, but you get the idea. It's very, very close to sitting in there on their own. Pretty pleased with that. With quality like that, I'm starting to make up for that silver soldering debacle. To drill the holes in the ends of these pieces, I set them up like this in the vise, both together, which has many benefits. Balances the vise jaw for proper clamping, and I only have to do one set of edge finding because they have the same y-axis, and I can use the absolute scale for one and the incremental scale on the other on the DRO. So I can do all 4 holes on one end of each part in a single setup, and the pieces are sitting down on the rails of the vise, not on the hole in the center, which is holding them vertical and square. And drill and tap, yada yada. Putting them back together as a pair now, I'm drilling and reaming a hole down through both of them. This is for a couple of pins that hold the suspension for the front axle box. And these pins need to be perfectly aligned in the final frame, hence reaming them in one setup like that. Speaking of those pins, I made those over on the lathe out of some precision ground tool steel. They just required having a little bit of a diameter turned on one end of each pin. Very, very simple. And Yahtzee. Those pins get Loctited into the cross members. You'll see how this all works here in one moment. After that Loctite set, then I can install them in the frame. So these get bolted to either side of the openings for the front axle box. So they form cross members for the frame to give it rigidity, but also create the pivot point for the axle box. You can see now why the width of them is so important, that they be identical, and that they be the correct length so they don't pull the frame out of square, and those pins have to be perfectly aligned so that they form a pivot for the axle box, which will sit in there like so. If you're wondering why the front and rear axle boxes are different, the rear axle is fixed in space and only the front one pivots. That creates 3 points of contact, which creates a plane, and the suspension is unsprung. That's a simplified design from the prototype, and that's what Kozo designed for this locomotive. Not all suspensions have to be sprung, and in a small locomotive model like this, it's sufficient that there be a little bit of movement in the drivers, but they don't have to be actually sprung. And just like on the real thing, all the connecting rods and so on have a little bit of pivoting motion in them so that the drivers can move independently. Locomotives do have suspension and the drivers do need to be able to move independently, so there's a little bit of pivoting action in all of the connections that are going to be between the piston and the 2 drivers and so on, as you'll see. But that is going to have to do it this week. That is all the time I have for this project. I hope you've enjoyed watching me finish up the structure of the frame. Thank you very much for watching. Thanks for sticking with this project. It's really getting exciting now as we get closer and closer to the valve gear and all the stuff that I know you're all waiting for. Thank you very much to all of my patrons for making all this content possible, and I will see you next time.